Hi everyone, I'm Chen Chongchang from National Tsinghua University. The topic of my talk today is ECS2, a fast erasure-coded storage system on GPU-accelerated storage with parallel and direct I/O. This is a collaboration with S3 platform and IBM, and Jerry Cho is my advisor. Here's the outline of this talk. I'll first talk about the background, objective, and contributions of this work. Next, the approach we proposed, the implementation of the approach, performance evaluation of this work, and finally the conclusion. As we all know, the data size has grown rapidly in recent years. This rapid growth of data creation translates to a huge demand for large, reliable, and cost-effective storage systems. But a large system size also increases the chance of component failure. So the technique to protect data become more important than ever before. To provide data reliability, RAID and erasure coded are commonly adopted in modern storage systems. Let's first talk about RAID. Take RAID 1 as an example. Data will be replicated into 2 additional disks. This system can tolerate 2 disk failures, but the additional storage needed is 200%. In comparison, erasure code can provide the same level of protection with less storage needed. Erasure code comes with coding configuration, NK, which means the data will be partitioned into K blocks, and then coded into N blocks in order to tolerate N-K missing blocks. Here, we use 6-4 configuration as an example. Only 2 additional data blocks are generated from encoding. So the additional storage needed is only 50% of the original data size. To decode data, one can choose any 4 out of these 6 blocks to reconstruct the original data. Therefore, at most 2 missing blocks are allowed. The setting of NK also provides fine-tunable level of protection to generate an arbitrary number of independently coded blocks. Therefore, erasure code have been widely adopted in many distributed and large-scale storage systems, including Azure Cloud Storage, Facebook Warehouse, and Ceph distributed file systems. However, adopting erasure codes does have one critical drawback, that is, the computation cost for encoding and decoding. Since all these operations mainly consist of matrix multiplication, they can be offloaded to accelerators like GPU to achieve much higher computing efficiency. For instance, here's a list of work to accelerate erasure code on GPU. libgplotr uses mathematical techniques and table lookup to achieve 5 to 10-fold speed up on GPUs over CPUs. P-Erasure uses XOR-based erasure code to reduce multiplication operation and achieve 2 to 4 times speed up over libgplotr. Later works like GCRS further improve data access pattern to achieve 3 times speed up over P-Erasure. All these works show significant performance advantages from GPU offloading. While all previous work aimed to minimize the coding time, we found the I/O performance has become the main bottleneck when using GPUs. As shown in the figure in the left, data must be copied from between GPUs and CPUs before encoding and decoding. As the GPU speed grows much faster than the I/O bus bandwidth, we could spend a significant portion of time on data transfer instead of computing and waste GPU power. Therefore, the goal of our work is to reduce the I/O delay by exploring the latest GPU technique to move data directly between GPU and storage devices as shown by the figure in the right. In sum, our work shortens the data path using GPU direct RDMA technique, and we implement our approach as an user-level library called ECS2, Erasure Coded Storage System, through our file system like APIs, users can create and access their Erasure coded files to obtain higher data reliability on any file systems, as shown by the figure in the right. Next, we compare and analyze 3 different approaches to detail the benefits of our proposed method. CPU refers to the method of coding on CPUs. GPU refers to the method of coding on GPUs and copy data through the host. GPU Plus is our proposed method with direct memory copy between GPUs and storage devices. We use file write and encoding operation as an example to illustrate the difference on I/O paths. CPU approach that CPUs directly access the file in host memory and write the encoded data to storage devices like SSDs. So its I/O time only consists of the coding time on CPUs and the data transfer time from host memory to I/O device. In comparison, the default GPU programming technique requires the programs to move data between devices through host memory. So GPU approach must first send the data from host memory to GPU for encoding, then send the data back to host memory before writing it to SSD. As a result, GPU approach will be faster than CPU approach when the coding time saved from GPU is much more than the extra time to transfer data between host and GPU, which is always true in most cases, because GPUs can easily speed up the coding time by more than the factor of 10. But obviously, the long I/O paths should be minimized to deliver better I/O performance. Therefore, in GPU Plus approach, we take advantage of GPU direct technique to reduce one data transfer and speed and send the encoded data directly from GPU to SSD. As expected, the GPU Plus approach will be faster than GPU approach when the data transfer time from GPU to SSD through memory is longer than the direct data transfer between them, which is always true in most cases, especially with the recent advanced technology of I/O systems like NVLink and PCI switch. The P2P connection bandwidth among devices has grown rapidly in modern computer systems. As a result, our proposed approach has 2 main benefits. First is to eliminate one data transfer from GPU to host and reduce I/O latency delay. Second is to reduce the computing and I/O loading at the host side, which can easily become performance bottleneck when multiple devices are installed in the storage system. Next, we will explain how we implement our approach by integrating 2 libraries: GDL copy and for direct data transfer in between GPU and SSD, and distributor for erasure coding computing. GDL copy is a library implemented based on the NVIDIA GPU Direct RDMA technology. It offers the infrastructure to create user space mapping of GPU memory, which can then be manipulated as if it was plain host memory. It sets the mapping between CPU virtual address and GPU physical address. So every data manipulation to the CPU address will be mapped onto the corresponding GPU address. We modify this library by adding the struct page to enable direct I/O bus address translation. So the data from an I/O bus address can be directly rewrite to GPUs. To use this library, we need to first pin buffer to expose the GPU physical address to the handle. Next, we call map and pass in our CPU pointer one wants to map with. After this operation, CPU pointer is mapped with the GPU address. For the file reside on SSD, we need to open it with O direct flag. We just simply need to read the data from the file that resides on SSD into the CPU pointer. So so that the data on SSD can be directly transferred onto GPU. We choose libjupyter as our coding library due to its source code availability and simplicity. libjupyter originally allocates internal maintained GPU memory. When coding the function, at the point of time, on-the-fly transfer data from host memory to GPU memory, thus the encoding, and send the data back to host. This does not fit our purpose, however, as we want to send the data directly to SSD, not host memory. To solve this problem, we need to integrate these two libraries. First, we allocate GPU memory in the user program. And for libjupyter, we pass in the GPU pointer we just allocated in the user program. Second, we utilize GDR copy to map the GPU memory with its corresponding CPU pointer. Now, we read in the encoded data through CPU pointer. The data will be mapped onto the GPU address. Third, we call decode function in libjupyter. Finally, we can copy the decoded data to our host memory. We evaluate our implementation with real I/O requests and trace to show the I/O performance improvement over existing approach under shared and multiple SSD environments. We conduct our experiment on storage systems with V100 GPUs and NVMe SSDs connected by a PCIe switch. If not indicated otherwise, the default size is 1 GB. And Erasure code configuration x64, the bandwidth between host GPUs and SSDs are summarized in the table. We can observe the I/O bandwidth of SSD is bounded by its data read-write speed. So the bandwidth between host and GPU is much higher. First, we can see in the plot, y-axis marks the response time of an I/O request from user's process. X-axis lists approach we measure. CPU approach takes a large amount of time doing coding. We can clearly see GPU does provide speed up. The yellow part, D2D data transfer, means the latency to transfer data in between GPU and SSD devices. Next, we zoom in on the GPU and GPU Plus part to see our proposed method performance. You can see for write with direct I/O, it provides 15% latency improvement, which is from eliminating one data transfer between GPU and host memory. And read gives 21% of improvement. Higher improvement from read was observed because SSDs have higher read speed than write. So the same time reduction from our approach results in higher improvement percentage on read time. After showing the performance improvement of a single I/O request, the last two sets of experiment evaluate our approach from overall system aspect. First, we consider there could be multiple applications running on our system. These applications could be some CUDA computing programs that wants to utilize the residual CPU capacity, or some I/O programs that want to read data from different SSD devices. In both usage scenarios, the bandwidth at host must be shared by all the processes and will become the performance bottleneck. So we want to show our approach can address this performance issue. To simulate the first scenario, we introduce a set of background tasks, which are dummy GPU processes that constantly issue the CUDA memcopy command to occupy the memory bandwidth. The plot shows how I/O performance from our storage system will be slowed down by the background GPU workload. Clearly, the I/O performance will be degraded as more background tasks are added. But the read and write performance of our approach with GPU Direct suffers much less degradation because our approach requires less bandwidth at host. In the second scenario, we evaluate scalability of ECS2 when parallel I/O are used across multiple SSDs. The plot shows the aggregated I/O throughput as our system utilizes more SSDs. Our system achieves a reasonable good scalability until the bandwidth between GPU and SSD is saturated. The scalability for read is worse than write because the SSD has higher bandwidth for read than write. Noted, our approach enables device-to-device data transfer, so the host bandwidth is not the I/O bottleneck. We can allow multiple SSD to utilize a single GPU for cost saving. Better scalability can be achieved if more GPU are used. Lastly, we use I/O trace to evaluate the overall system throughput when multiple I/O requests are issued. The I/O trace is from Sister 17. We take a few columns from the experiment, namely timestamp, I/O type, either read or write, and I/O size. We simulate the request stream scenario by maintaining a sorted request queue, which is sorted by the arrival timestamp of each request. ECS2 processes the request one by one in order, and will process the request only when the current timestamp is later than the request arrival timestamp. We simulate heavier workload by shortening the inter-arrival time of requests. As requests are sorted by arrival timestamp and processed in order, requests will queue up when ECS2 cannot deal with the request in time. Hence, we define two performance metrics: the response time as the end-to-end I/O time and process time as the I/O time excluding waiting time. These two lines are the improvements comparing GPU and GPU Plus approach. Y-axis is the time reduction from GPU Plus. X-axis is the workload level. Let's first look at the red line, the process time improvement. This line shows the latency improvement we can get purely from GPU Plus approach compared to GPU approach without any queuing effects. The time saved stays pretty much the same, around 20%. The blue line, however, is the response time improvement. It starts to grow when the workload gets heavier. This means our approach is getting more beneficial. This is because GPU Plus approach can deal with the request with shorter latency, reducing the amount of requests in the queue, avoiding accumulated wait time to grow exponentially. On the other hand, GPU approach deal with the request with longer latency, and the queue builds up. As we can see in the plot, when the workload level is around 3, even GPU Plus approach cannot deal with the request in time before the next request comes and starts to queue up, mitigating the benefits it brings. As we further increase the workload, the wait time will dominate the response time, further reducing the I/O response time reduction. Our approach can not only reduce I/O time for a request, but can also achieve higher performance improvements for the overall systems. To conclude this work, our work investigates GPU accelerated Erasure coded storage system and identifies its I/O performance issue. We propose a new method that uses GPU Direct to reduce I/O path and avoid potential host bottleneck. We achieve our goal by integrating GPU Direct and GPU accelerated Erasure code library and implemented our approach as an user space library. Our evaluation showed that for a single request, we have 15 latency improvements for write operation and 21% for read. The overall system throughput under real I/O workload can reach up to 70%. Our implementation also has a good parallel I/O scalability using only a single GPU, and strong resilience to user GPU workload, so the GPU utilization can be maximized. Thanks for your attention.